Hello, welcome. Now let's consider an efficient and a powerful approach for automatic differentiation through implicit numerical schemes. This can be used to train neural networks where you use a very complex numerical solvers. And this is called the physics constrained learning. And this material is optional. So if you have a hard time understanding that and do not have too much time, you can just skip this section. And physics constrained learning, instead of penalty methods or residual minimization methods, it solves for you first using numerical solvers in the PDE constraint optimization. So let me describe the procedures first and then have some discussion for physics constrained learning. The first step is to solve for U, where you have this PDE system. So you can solve for U using any numerical solver you have, for example, finite difference or finite element or any other schemes you have. You might use implicit schemes or explicit schemes, or spectrum method or any method. And then you solve for U and get an expression like this. You cannot write out analytically in many cases, in most cases, but you know that your solution U depends on theta, where theta is the weights and biases of this neural network. The second step is that you want to solve the unconstrained optimization problem instead of the constrained optimization problem. This is done by just plug the solution you have into the objective function. Note that you cannot write this down explicitly. This is just a notation here. You can calculate this quantity using numerical solvers. And this step, if you want to solve this unconstrained optimization problem using gradient-based method, this requires you to compute the gradients, that is partial L tilde, partial theta. And I use a tilde here. In the original formulation, I do not have a tilde because that has the dependent variable U. Here, the dependent variable is theta. The challenge here is to compute the gradient efficiently and automatically in the computational graph. So let's see how we can compute this term in a computational graph. First of all, let us consider a simple example. Here, you might have a numerical solver to solve U from the right-hand side Y, and this is the coefficient matrix. And the theta is a scalar here, and A and B are matrices. So you solve this equation for U, and you also have your observation for U. And you want to minimize the observation of U and U naught with respect to theta, and to find the optimal scalar. And this is, you can actually solve that by hand, but here let's consider solving it using physics constrained learning. And by definition, this L tilde should be U theta minus U0. And U theta is the solution to this equation, where U depends on theta, but we'll assume that you cannot just write out U theta analytically. Although in this case you can, because this is U is just equal to A plus theta B inverse Y. So let's consider another problem is how to compute the gradient of this L tilde with respect to theta. So let's consider an implicit function theorem, which is maybe in your first year calculus or second year calculus or so. And in this case, you have a function f, which maps x to y, and it is implicitly defined by this formula. And you cannot compute the y explicitly in terms of x, although you can in this case because you have the cubic formula, but we assume you can't. And you want to solve that numerically using, for example, the Newton's method or bisection method. And you can treat y as a function of x if you want to compute the gradients of y with respect to x. And this is what we do in the calculus course. And we treat y as a function of x and take the derivative on both sides with respect to x, and you get this formula. And you rearrange the expression, and you finally get this y prime. And this is pretty simple. And the problem is, can we apply this technique to computing the gradients here? Yes, we can. And this is done by first take the derivative of L tilde with respect to theta. And this, because L tilde is just the square, and so you have this formula, and you have u theta minus u naught, and you also need to compute this term. And to compute this term, you need to go back to the PD constraint optimization problem. And this is the PD constraint. And we compute the u theta out of this formula. So like the implicit function theorem, we treat u depending on theta, and here is also theta. And we take the derivative with respect to theta on both sides. So we get this formula. And we rearrange that and solve for u theta. So we get this formula. And finally, we just put them together into this equation and get this formula. So this is how we compute this gradient. And yeah, and actually, actually there are two ways to compute this formula. The first one is to compute from right to left. The second one is to compute from left to right. So which one is a good way to do that, or are they equally good? So let's go back to the reverse mode AD. We already introduced the reverse mode AD, and in reverse mode AD, the gradients are always backpropagated from downstream, which is the objective function, to upstream, which is the unknown. And in this case, the gradient should be backpropagated in the order from left to right. That is the order from downstream to upstream. So the first step is to compute this term. And if you write it down, and you never need to solve, you never need to compute the inverse of this matrix. Actually, you only need to solve for linear system, where you have A plus theta B transpose G equal to u theta minus u0. You solve for this matrix. And one observation is that if you look at this PD constraint, you solve A plus theta B u theta equal y, and here you solve for A plus theta B transpose G equal something. And you also need to solve a linear system. But in this scenario, the linear system is an adjoint matrix of the original linear system in the PD constraint. And this is not a coincidence. This is always true if you do something like this. So they have some deep connection with the so-called adjoint state methods. And in the adjoint state methods, they usually solve adjoint matrix of the original problem, and that's why they call it adjoint state methods. And yeah, they have some deep connection with adjoint state methods, but we will not cover that in this lecture. And finally, if you solve for G, you get this formula. You plug in and you get this formula. That's not done. You also have a lot of methods to compute that. For example, you compute this first and then compute this term, or you compute u theta first and the G transpose here. Now we have a trick to do this very efficiently and conveniently. That is using automatic differentiation. Here's a trick for evaluating G transpose B u theta. And if you will look at this formula and look at this expression, you will find that actually G transpose B u theta, if you bu without a theta, without take the derivative without taking the derivative with respect to theta, you will get G transpose Bu, which is a scalar. So to compute this, you can just take the gradient of this scalar with respect to theta. So this is a magnitude 1 mapping. What can you do with that? Yes, the reverse mode automatic differentiation. And you can take the derivative of a scalar with respect to a vector, and that can be done very efficiently in reverse mode automatic differentiation. And actually, technically, this is done using the so-called TF dot step gradient in TensorFlow, or the independent function in ADSMB. And they are actually the same function. And using this technique, the computation can be very efficient and useful here. So let's consider the more abstract case where you have our PD constraint is written in a very abstract way, where you have f operator, which is high dimensional map from U to the residual of the numerical solver, and you also have a theta parameter, and L is a function, is loss function depending on U. And in this case, you first solve for U out of this f theta U, and then you plug into the loss function, and you get L g theta. Okay, so this is the first step. Very simple. You just solve for U from this equation and plug into L, and you get a L tilde. The next step is to take the derivative with respect to theta on both sides of the original system here to extract the gradient of partial g with respect to partial theta. And in this case, you treat UH depending on theta. So like this, you take the gradient with respect to theta on both sides of this PD constraint, and then you rearrange this equation to extract the gradient of g theta with respect to theta, and then you get this formula. You are not going to compute this inverse here, nor you are going to computing this term immediately after you get this term. Instead, you plug this term into the expression for partial L tilde with respect to theta, and you get this formula. And you plug in, then get this formula. So for automatic differentiation, the case is that you compute from left to right. So you first compute this term, and to compute this term, you are solving a linear system just like this. Instead of solving, instead of doing the inverse first and then do the multiplication, then this will be a vector. And to this vector is multiplied. You then do an inner product of this vector with and this vector, because this is actually a this is actually a matrix now, and with this matrix, instead of computing the matrix vector production, you do some similar trick here. And here you just treat g independent of theta. Here is just like you treat this term independent of theta, although it is dependent on theta. But for this trick, you treat this theta independent. This f is independent of theta, and then you do the inner product of this scalar and this f theta u vector, and you get a scalar, and then you get a vector because you do an inner product, and then you take the derivative with respect to theta over this scalar, and then you get the gradient. And the next step can be done using automatic differentiation. This is how physics constraint learning works. It works similarly with the automatic differentiation system, and this also works for implicit numerical solvers. As you can see, we did not have any assumption on the form of a numerical solver. So your numerical solver can be explicit or implicit, and a numerical solver can also be very complicated. You have to solve a bisection algorithm or Newton's methods in your numerical solver, but still you can compute the gradients very efficiently and automatically.